So we are starting this session. First speaker is Michel Perelstein. Yeah. He is going to talk about multi-partied continuous variable entanglement generation using Josephson metamaterials learning. I'm sorry about that. Okay, you may start.
Yeah, thank you very much. Yes, so first of all, we'd like to thank, of course, the organizers and all of you, so you stay for the last day of the conference to participate in this session and to listen to this talk. So yeah, my talk will be about the multipartite entanglement generation and using, in particular, superconducting quantum circuits. And the basic element that we used, of course, Josephson junction, and therefore we're using materials that we call Josephson metamaterials. And that work is done at Aalto University, and all the measurements were performed at Aalto University in Finland. And the fabrication of the samples was done by the VTT, which is the Finnish Center for Technology, and maybe you're familiar with that. And also right now, I'm also working at Terra Quantum, so it's a Swiss-based company, but this work is done only in Aalto and VTT. And right now in Aalto University, we have multiple groups and the open positions for PhD students and postdocs. So if you know someone and someone in your group, will be nice to have them, and please write to Dr. Sorin Peruano, who is the group leader at Aalto University. So let's then go deeper into the basically multipartite entanglement. So essentially what can be done using entanglement in quantum technologies we're already well aware of, and multipartite entanglement is basically a resource that we can leverage for multiple applications such as computing, sensing, or communications. And basically, this multipartite quantum entanglement can be used as an additional resource for quantum devices, for existing quantum tools, such as optical or superconducting devices, for instance, based on the artificial multi-level atoms, such as qubits or qubits. And then multipartite entanglement can serve as a, let's say, sort of mediator for the interaction between different parts of the quantum processing units, for example. But of course, this system that generates multipartite entanglement at this certain states can be used as a basically separate quantum engineering toolkit, so we can perform measurement-based computing based on the multipartite quantum entanglement or distributed quantum sensing, but I will tell about this later. And of course, there are different approaches, and of course, in optics, people quite advanced with the multipartite entanglement generation, and there'll be some work that people generated and different groups generated multiple modes, like dozens, even hundreds of modes, so really large states. And of course, this is in terahertz range, so it's compatible with the current optical quantum devices. But of course, some of these, especially, kind of optical setups, they could be pretty complicated, so it's not like a single system on a chip, and the complicated tuning is required. It may be pretty challenging. And of course, the frequency range is not compatible directly with superconducting devices that are probably the most advanced devices for computing, at least. And of course, in microwaves, there is a kind of urgent need to generate multipartite entanglement as well, because frequency range is suitable for superconducting QPUs, and it can be used in connected to the superconducting QPUs, but also in the communication open space for certain detection problems. Entangled microwaves is also a very, very promising tool. And of course, with microwaves, since your system is basically system on a chip, then simple tuning may be required only, and then of course, it is a nice platform. But of course, there are several engineering challenges, and of course, now we have limited number of modes, and all this kind of only started, and it's ongoing process. So basically here I will tell about the platform for the generation of the multipartite entanglement in microwaves. And why we're interested in microwaves. So of course, there is multiple applications, as I mentioned, such as networking. In the distributing superconducting quantum computing is also kind of a hot topic. So here you can see an example where we have, not we, but a group in the ETH, they had two fridges, and they connected through a huge tube, and then they try to entangle, let's say, different systems through this tube. And of course, in some kind of the distributed quantum computing platform, that multipartite entanglement can be used. And of course, it can be used also in the distributed quantum sensing, where we have different microwave probes, and we basically have a certain, let's say, signal-to-noise ratio that can be potentially improved once these microwaves are entangled and not just separable states. And of course, plenty of quantum optics phenomena can be studied using these microwaves, so it's a really, really nice platforms and applications. So basically the system that we mostly use for kind of the entanglement generation study, it's called Josephson parametric systems or Josephson parametric amplifiers. And we've been working with them for several years now, and the different theoretical work published in Alta and now experimental works as well. So basically, the Josephson parametric amplifier is very, very simple circuit. So you just basically a squid loop shunted by the capacitor, let's say. So it's basically an oscillator, but we're trying, of course, to focus on nonlinear oscillators. So it's a nonlinear medium that we can interact with. And this device is often used as an amplifier. So basically, what is happening is that we have an input signal that goes into this kind of oscillator, then it reflects back, and the reflected signal is like with different properties. And if we want to utilize this device as an amplifier, so basically we have a certain, let's say, additional line that we use as a pump for our signal. And the idea here is to transfer energy from the pump that we guide through, let's say, flux to squid. It's one example how it can be transferred to flux parametric signal, flux signal to the squid loop. And then we transfer the energy to the signal that reflects back, and that's amplified. So if we adopt and tune the frequency, we can get a parametric amplification just as regular mechanical parametric amplifier. And of course, these devices, they're relatively simple, and you can play with different basically quality factors of these oscillators, and then the question, how do you want to couple that oscillator with your kind of environment? And for instance, if you just couple it directly, so you'll have a low quality factor, but it is actually pretty good for the broadband gain, and we demonstrate that you can fabricate very, very simple circuit and get pretty broadband gain that can be used for readout of QPUs, for example. However, if we want to kind of generate quantum states, we would like to have high quality factor, so to generate high quality entanglement, and therefore the device that we considered is basically we added certain capacitor, coupling capacitor, and then we can consider just a waveguide that is shunted by the squid loop. And of course, the amplification is kind of nice, and it was studied like for the last decade, so it's pretty clear. But actually, this system can be used in the same manner as nonlinear crystals are used in quantum optics. So in nonlinear crystals, if you do not send any signal in your system and you send just a single pump, so basically what you do, you upconvert your vacuum states, and you generate additional, or not additional, but you generate pair of photons. And you generate signal and idler photon, and you can prove that these photons can be entangled. And that's kind of the way how you can generate bipartite entanglement. If you now apply multiple pumps, so you actually generate multiple photons, and all of them share basically the same entanglement, so they were born into kind of existence at the same time for the same media, nonlinear media, and therefore there is a certain entanglement. And of course, the properties of this entanglement, the structure of this entanglement is fully defined by the pump configuration. So the frequencies, the amplitudes, and their phase shifts. So you can describe it pretty well theoretically by writing down all the kind of necessary equations of motions, considering Hamiltonians. For bipartite, it's pretty simple. For multipartite, it's tricky to solve it analytical, so we basically solve it numerically, but in this work we also provide a simulation based on kind of numerical analysis of these quantum Langevin equations. But basically, what is multipartite entanglement in that case? So here, essentially what we do is that we consider a single resonance of the Josephson parametric amplifier, and then within this resonance, we send multiple pump signals. And I want to emphasize here that we actually utilize pretty high frequencies for the pump. So here we consider in particular free wave mixing. So it means that we generate corresponding states at the frequency which is half of the pump of the frequency. So if we apply a single pump tone in our kind of JPA resonance, then we can generate pair of, that's a signal and idler mode, and then these modes would be entangled. If we now apply multiple pumps, then we can generate multiple modes, and these modes are somehow artificially defined in here. So basically we just specify the width of the mode and then kind of the shift in the frequency space, and then basically we can generate certain multipartite entanglement within our JPA resonance. And here you can see basically the circuit, so it's very, very simple. We just have certain pad, then we have a resonator shunted by the squid loop. We guide our pump in here, so we apply multiple pump tones, and as an input we have just vacuum state, nothing goes into this system, but on the output we basically measure corresponding microwaves, and then perform the corresponding analysis. So that's more kind of extensive description how this experiment is performed. So maybe I will not go into much details, but once again, here we have a chip. We guide our pump to the sample, and then we guide out of the fridge, so it will not interact with anything. Then we basically capture the whole kind of microwave range that we're interested in, and usually we operate from 4 to 8 gigahertz frequency, so like usual frequency for superconducting devices, superconducting qubits. Then we perform measurement using a chain of amplifiers, and then we analyze corresponding quadratures. So here the goal is, of course, to analyze the quantum state. And of course, like multipartite entanglement is quite broad topic. So here we in particular focus on the tripartite entanglement, so where we define 3 modes, and 4-partite, or tripartite and quadripartite case. And in tripartite case, we applied 2 pump tones, and then we specified 3 kind of spectral modes that will be analyzed on the entanglement. And in quadripartite, we applied 3 pump tones and then analyzed modes. And as you can see here, the JPA that we're working with, it has very narrow band because it's kind of the high quality factor device. And here the kind of bandwidth is only about 7 megahertz. So we basically define these modes like 2 megahertz, less than 2 megahertz bandwidth. And the quadripartite case, we kind of squeeze them and define less than 0.5 megahertz. And that's kind of an arbitrary, so we can define these modes as we like, and then basically fit as many modes as possible. And the frequency that our device is operating on, so here you can see the kind of DC frequency with the external flux. So we can change the base frequency of our device by using external flux. And then once the point is fixed, we can basically trigger these parametric processes by the frequency, which is basically doubled as the operating frequency. So we work on frequencies about 6 gigahertz, and then generate tripartite and quadripartite states. And regarding the analysis, so essentially these states, it was shown multiple times, and we also verified this, that these states are Gaussian. So it means that we do not actually need to measure the whole density matrix and to characterize these states rigorously in that way, but we can just deal with the covariance matrix because we're really interested only kind of in the pair correlations. And basically what we do here is that we perform a certain necessary calibration that is needed here. Then we define corresponding quadratures. And once we define basically the quadratures, we can compute the variances and covariances and create the correlation matrix. And that correlation matrix is full enough to characterize the quantum state. And the way how we do this, how we basically construct this matrix is the following. So we measure the whole signal that goes out of the device, so at certain band, and of course it's defined by, let's say, the sampling rate or something like our measurement setup. And then we basically measure I and Q quadratures, and of course we capture that signal in time. Then we combine them as a single complex signal. And then we perform the Fourier transform, and now we are in the frequency domain. And in the frequency domain, we can artificially specify corresponding modes that we're going to look into. And then once these modes specify for each mode, for each kind of this window separately, we can again perform inverse Fourier transform, go into the time domain, and compute corresponding correlations between different modes. And by doing this for I and Q quadratures separately, we construct this covariance matrix, and then we can perform the analysis. And if in the bipartite case where we have 2 modes, it's very simple, so it's either entanglement or not. In multipartite entanglement case, it's not as simple anymore. So there is a multiple structures out there. It could be pretty complicated and cumbersome, but basically there is a PPT criteria, and of course it is used for analyzing the bipartite case, but you can generalize it and basically compute the corresponding eigenvalues of your covariance matrix. And if those eigenvalues, let's say less than 1, then basically you get yourself a fully inseparable state. And that's sufficient for only kind of pure states. And however, there are states that are, let's say, a mixture of separable states. And this state is kind of not so-called generally entangled. So they will introduce a term, a genuine entanglement. So basically you want to eliminate these states as well. So you want to have like a pure genuine entanglement. And there were different criteria introduced by Van Luck and Furzawa work, but there was a nice kind of criteria in Teh and Reed paper where they basically perform this analysis of different covariances and introduce just a single number that can characterize whether you have entanglement or not. And we basically use this criteria to characterize whether we had genuine entanglement or not, because that's kind of our final goal. And let's say that is the most complicated entangled state to create. And here's the example of the kind of experiment. So we also perform the simulation as well. And here we basically evaluate this kind of entanglement criteria number, a single value. And if it's less than 1, then we have genuine entanglement. And then what we start to do is that we apply, so in tripartite case, we had 2 pumps. So we apply 2 pumps at a similar pump amplitude. Then we start to vary pump amplitude and see how the criteria changes. And in the beginning, you can see that it is around 1, so it's kind of too weak basically to characterize. But then once we kind of start to increase the power, we see that pattern. So at first, the state is entangled. And when we increase the power more, then we basically lose our entanglement. And the same for kind of the same behavior is for different phase difference between pumps. But basically, you can play with these phase differences and construct the entanglement that you want. And for the quadripartite case, it's too complicated, so we just optimize over all possible phases. So here is just kind of one behavior. And here you can see that we also verified that you can generate 4-mode state that is genuinely entangled. And you can play with this structure. You can get, let's say, fully inseparable state, but not generally entangled. So basically, there is a possibility, and here is like a toolkit that you can use to construct the state. And here is the example of the covariance matrix that we analyze. So by looking at this, it is hard to judge what is happening there. But then applying all these criteria that involve some optimization, you can decide whether it's genuine entanglement or not. And of course, in terms of the, let's say, application for the quantum computing and for the, let's say, measurement-based quantum computing, it is interesting to analyze what are the states that we generated. And usually in literature, you can find the term like H-graph states, so basically states, Gaussian states that were generated by certain Hamiltonians, and the kind of corresponding correlations between different modes defined fully by the Hamiltonians and very particular Hamiltonians. And basically, you can, let's say, write down your Hamiltonian in the following way, and then you have adjacency matrix that defines your graph. And usually, this H-graph, they include only 2-mode squeezing. So once you have a pump, and then you have 2 modes, and then you have another pump, another 2 modes, etc. But in our case, what we do is that we actually apply these pumps simultaneously. So it means that we generate actually more complicated correlations than just like 2-mode squeezing, like step by step. So we generate a different type of correlations, which in the literature could be called like beam splitter, because it's similar to what is generated when you have 2 beam of light that interacts on a beam splitter. So it's kind of a similar but not the same type of correlation. And here you can see the example of these kind of graphs. So A and B is basically what we generated in this work. So we generated, since we have pump between 1 and 2 and between 2 and 3, we generated 2-mode squeezing between these corresponding modes. But we have also another type of correlation, the beam splitter, that is generated effectively because of this simultaneous application of pumps between 1 and 3. So we kind of conclude the graph. The same for the 4-partite case. And we also demonstrated theoretically that you can apply more pumps and then generate only 2-mode squeezing everywhere. And then you deal with something like GHZ states, so that can be utilized then for, indeed, measurement-based computing. But this what we call generalized H-graph states, so it is not limited by 2-mode squeezing. More complicated correlations can be introduced, and theoretical analysis is kind of presented in the paper. And here, if you can compare it with optics, so here actually modes are not interacting directly, right? So we don't have actual beam splitters where they interact. So basically, it is happening with the same nonlinear environment, and all this kind of entanglement is happening because of the basically absorption and then emission of correlated photons. So, however, there are several questions still open. So it's a nice platform, but how to overcome frequency crowding? Because if we deal with 7 megahertz, we cannot place, I don't know, 50 modes there. We cannot basically separate them from each other. It's become too dense. So the next question is how to get entangled microwaves at desired frequencies, because here, okay, our device works at 6 gigahertz. We can design another device that works at 5 gigahertz. But if you would like to get entangled photons at 4 and 8 gigahertz, It's a really interesting question, so how to get them at desired frequencies. And then also how to separate them physically. Because for multiple applications, especially sensing, you would like to have a separated in space. And if you have them so dense, it is just impossible to design so narrow filters, so very, very challenging. So the idea is to use another device that is called the traveling wave parametric amplifier. So it works similar but in a different manner. So Josephson parametric amplifier is a cavity-based amplifier, but traveling wave amplifier, that's a very complicated device. So it consists about 5,000 Josephson junctions, and it contains a certain element that is called superconducting nonlinear asymmetry elements, snails. So and then you have more than 1,600 of these snails in the device, and basically if you want to operate it as an amplifier, you send your signal into this domain, and you send the pump as well. So now the pump is not transferred through the flux, but directly kind of inside the device. And then you can design your media in such a way that the energy of the pump will be transferred to the signal, and the longer the amplifier, the higher you get the gain. And we designed, or not we, but actually VTT designed the device that is based on a free wave mixing again. So here you send the pump that is kind of the frequency is twice as the signal frequency. And then again, you can have the same effect as you observed in Josephson parametric amplifiers. You applied your pump, and on the half of the pump you have signal and idler, and they could be entangled. So basically here you can see the results for the amplification. It's not very interesting for this topic of my talk, but basically we generate like 13 dB on average from 4 to 8 gigahertz, which is really good for and really broad band for amplifier. And here you can see like all band from 4 to 8 gigahertz, and the amplification is pretty high. And you can suppress this kind of ripple profile by suppressing slightly the pump power and get nicer and more stable profile. And here basically the scheme, how we utilize these devices to generate bipartite entanglement. So here our focus was basically, we would like to start with a bipartite entanglement, but with modes that are separated from each other as much as possible basically. And here we have our device, so we send only the pump signal inside our device, then we cut out this 2 omega, which is the pump signal, measure this omega, and then basically, since now we're operating with really broadband signals, we need to kind of cut out these frequency modes, not artificially in the code, but physically. So basically we captured the whole signal before, but now we captured only corresponding modes. And then we also construct the covariance matrix. Here's a slightly different construction because now this device is not like it's a distributed device, so it's pretty long, so we need to take into account also internal losses that we calibrated in advance. And then these internal losses, knowing them, we can calibrate the covariance matrix. And here you can see basically the results on this kind of the performance of the device. So here is the bipartite entanglement generation, and we analyze like usual symplectic eigenvalues, and the logarithmic negativity was just again a single number that tells you if it's larger than 0, then your state is entangled. If not, then you don't have any entanglement. And with the low pump powers, no entanglement is observed. Then we see the entanglement, and then it drops down because we introduce more nonlinearities, and basically it's what usually observed with these devices. At high pump powers, you just lose your behavior. And we also repeat this experiment for 2 gigahertz separation, which is very impressive separation between modes, and you basically see the same behavior of the logarithmic negativity, so it's still present. We also observed 2-mode squeezing, and the 2-mode squeezing was better than 3 dB, but around that time. And here also we basically tried to separate our modes as much as possible. And here what we observed is that we basically found the best point, which is 4.8 gigahertz center, and then you try to basically separate your modes around this frequency. But of course you limit it by basically your experimental setup, because our setup is from 4 to 8 gigahertz, and we're limited by this kind of lower band because the lower mode is at 4 gigahertz, so we shifted to 6 gigahertz. It's slightly worse, but still you can see that we can separate our modes at 4 gigahertz, which is huge, and they're still entangled because the logarithmic negativity is still like 0.3, so it's not 0. And actually that was done in 2021. So, and then several works appeared. So one work, for instance, the beautiful work from Nicolas Roch group, who is the next speaker. And they also observed the 400 megahertz separation between two modes in a also traveling wave parametric system. And the experiment was a slightly different configuration done in the MIT group and Will Oliver group when they also observed about 2 gigahertz separation, which is also huge. So this device, I verified it to basically utilized as an entanglement generator. So basically here our goal was to create a cryogenic microwave entanglement generator. So what we did is that we demonstrated the generation of the entanglement, the structure of this entanglement between these multiple modes with these multiple pop schemes by tuning its corresponding parameters. And we also demonstrated that it's possible to separate these frequency entanglement modes over substantial, like 4 gigahertz frequency, maybe even more because we were limited by our measurement setup. And then you can basically fill all this band with your modes and then operate them. So the next goal, of course, is to increase the number of modes to perform physical separation, so that can be used for detection and sensing. And theoretical exploration is required to analyze the structure of the entanglement to understand what can be used for computing distributed sensing and, let's say, the communication between different modes. So all these results are outlined in these publications. Here is some pretty old ones, this theoretical publication. This publication appeared, I think, 2 days ago, so just recently, and this one appeared in like a few weeks ago. So all these are pretty recent results. Yeah, I think my time is over, so, oops. Yeah, so thank you for your attention.
We are open for questions. Are there any questions from here and from online, maybe? Yes, please.
Yeah.
Fully unseparable, inseparable, and genuine.
Yeah.
And what is the parameter which characterize this moment?
Yeah, so basically here what we would like to do is that, let's consider, for instance, three-partite case. So we have party 1, party 2, and party 3. And then we would like to basically analyze correlations between them. So the idea is that, like, of the genuine entanglement is that you cannot write down your state as any mixture or combination of separable states. So genuine entanglement is that when you cannot do this. And genuine entanglement is like the only, I would say, real entangled state, so to verify. But if you try to generalize the bipartite entanglement criteria, then you get basically fully inseparable states, which might be not, let's say, sufficient for certain applications, but basically the application is still to be explored. And I think in this paper, they explain quite nicely like what's the difference between genuine and fully inseparable and how it works in like on theoretical level.
And maybe second small question related with schema in which you include two similar Josephson junction and alpha. This one similar to qubit schema, but in your schema,
yeah.
What alpha? What is about?
Yes.
For
Yes.
This one.
Yeah, that's a very good question. Yeah, thank you. So actually, this scheme is very, very similar to flux qubit, right? Where we have two wells and then we can operate within two wells. But of course, the form of the potential, it depends on the alpha itself, right, of the junction size. So actually, in our device, we're trying to work with a single well. So it's not two-well potential, but single well potential.
A single.
Yes, yes. So it's not a qubit. So I mean, all our devices they're in the ground state all the time, and then we basically can utilize this device to play with nonlinearities in our traveling wave parametric amplifier, because that's DC additional signal. So unfortunately, I didn't have time to explain this, but this DC additional signal is used to tune nonlinearities, and by tuning these nonlinearities, we can get rid of the Kerr nonlinearities, which is the high order of nonlinearity, and then it that elimination of this nonlinearity help us to generate kind of the high quality entangled states, and that's quite important because, for instance, if you change the nonlinearity, you will lose all the entanglement. So that's quite delicate system.
Thank you. Thank you.
Are there any questions? Actually, I want to ask you two questions. One of them is, you are using pump word, and it's like, actually, in my opinion, it is pulse. Are there any difference between them?
So actually, we're operating our devices in continuous mode. So we're basically sending pump signal, and it's like constant generation. So we do not like send pulses in our devices.
You're not taking out, I think.
So what we do is that maybe that's good. So basically what we do is that we have a certain, let's say, I don't know, RF generator, and then we basically guide this RF in our device, and it's constantly on. So that generation is kind of continuous generation. So we can capture then the output and verify that these continuously generated states are entangled.
Okay. Actually, I'm wondering about the radio frequency range.
Yeah.
Are there any additives of microwave entanglement on the range, actually?
So, I mean, the range that we work in usually it's from, let's say, 4 to 8 gigahertz.
No, as a, area range.
As the area range,
Yeah.
yes. So with the JPA, that's kind of the lumped element device. So it's much smaller than the wavelength. But in traveling wave parametric amplifier, it's more complicated. So yeah, our traveling wave parametric
Are there
amplifier.
any additives of, microwave entanglement on the range? Do you think it is strange, maybe?
Yeah. So in Josephson parametric amplifier, I think, since it's much smaller than the wavelength, then basically our entanglement is kind of generated at a, let's say, single point, right? So we basically. But with the traveling wave parametric amplifier, it's really good question. So actually, it's a distributed system, and of course, these kind of microwaves or these upconverted photons, we do not know exactly where they were born, right? So we basically needed to consider the distributed nature of kind of gain and losses in our tupa. So we also performed some theoretical analysis on this. But basically, you can take into account the losses of your tupa and, let's say, take the worst case scenario consideration to verify that the entanglement was indeed created. But where exactly it was generated, we unfortunately don't know. Yes, it's a good question.
Yes, please.
Do you have any idea how many photons you generate? And can you measure, for example, the Fox state, like beyond this just correlators?
Yeah, so regarding the rate that we generated entanglement, so of course we need to kind of calibrate everything with respect to the kind of the device, right? So we actually do not generate entanglement at the room temperature, so it's all on the cryogenic setup. And here basically we also, in the work on the JPA, we provided certain estimate how basically on the kind of flux of the photons, so how many photons are generated per second. And what we also introduce is kind of entangled beats per second generation. And that also depends on your kind of bandwidth that you take into consideration. And I don't remember exact numbers, but I think it's like about giga entangled beats per second. But that's mostly comes from the bandwidth of the device. But regarding the Fox state, so we never thought about this and never tried. But I think it might be possible to try. Yes.
Okay. Are there any questions more? No. Thank you.
Yeah, thank you. Thank you very much.
Next speaker is Nicholas. I think he is going to join us from online. Nicholas, are you there?
Can you hear me?
Yes, I can hear you. You may share your screen.
With pleasure. Do you see my screen in full size?
Let me look at this just a minute. Yes, I can see.
I see my own screen on your own screens. That's interesting.
Yeah.
Okay, good. It seems it's in place now.
Okay. You may start.
Very good. A good morning, everyone. First of all, I would like to thank the organizers for giving me this great opportunity to present my results. Unfortunately, I cannot be with you in Bodrum. I got some little health issues very recently, so I could not make it to Turkey, even though I was really looking forward to joining you in person. Anyway, as I said, it's a great opportunity to present my recent work, and I hope we will still be able to interact, even though I will give you this talk online. Of course, if you want to discuss further these results, I'm happy to talk via Zoom afterwards or during the question session. So my name is Nicolas, and I work in Grenoble. By the way, do you see my pointer? Okay,
Yes,
good.
we can see.
So today I will not discuss mountains or snow. I will speak about our recent observation of dual Shapiro steps in a Josephson junction array. So, but before we jump and dive into science, I would like to introduce the team. And more specifically, it's very important to acknowledge Samuel and Nicolo, who are respectively the PhD student and postdoc working on this project. They are really the main driving force, and I'm here to report their work. As I said, this is of course a bigger collaborative effort, and I would like to thank my colleague Olivier, Kater, Denis, and Wiebke, who again provided a very important input and effort for this project. I also want to mention that Kater was with us in Grenoble for 6 months as a visiting professor. He is a professor at Washington University in St. Louis, Missouri. All right, so let me start with a short introduction. And the idea of this project is a bit broader than the dual of Shapiro steps, even though this is in itself a very interesting topic, of course. The idea is to somehow deal with the quantum metrology electrical triangle. And for those of you who are not familiar with this, let me give you a few hints. First, let's represent this kind of metrological challenge as a triangle. So the idea is to link 3 electrical units, namely volt, ampere, and hertz, via some quantum effect, or at least via some effects that are not depending on the size of the device, the way you perform the experiment. You really want to link these 3 units just by fundamental constant. And there exist already at the metrological level 2 legs that are covered. You probably know that voltage and current are linked via the quantum Hall effect, the quantum resistance. So I think now in the quantum Hall effect, integral quantum Hall effect, they are very nice plateaus, very flat. So you can really link voltage and current very accurately. Now, regarding the link between the frequency and the voltage, there is, of course, the AC Josephson effect and the famous Shapiro steps. So the idea is the following. You current bias a Josephson junction, and then you shine some microwave. So this is the IV curve, I mean the VI curve, I should say, without any microwave. And then whenever you add some microwave, you see some steps appearing. And what is remarkable is that these steps are quantized, and these voltage steps, they are exactly equal to an integer number times the flux quantum times the frequency. So as I said earlier, you see there is a direct link between frequency and voltage, and there is nothing but fundamental constant in between them. So this is also very nice. This works very robustly. Many metrological institutes around the world are using this effect. Now they are even making very long arrays of junctions to get even higher accuracy. I mean, that I could give a whole talk just about AC Josephson effect. However, this is not the topic of today. Today, I will show you how we could deal with the missing leg. So namely linking hertz or frequency and ampere or current. There have been many attempts in the past using single electron pumps in quantum dots, surface acoustic wave, or even superconducting electron pumps. Again, that could be a whole talk. There is a beautiful review if you are interested by Pecola and co-workers. So this is a very active topic, but so far this, let's say, technique, they were not based on a coherent quantum effect. So our idea is to find an alternative to these pumps, and this is what I will show you today. All right, so let me start with the AC Josephson effect and give you a cartoon of why do we observe these steps. So if you current bias a Josephson junction and look at its phase dynamics, it is very similar to what you would have in a washboard potential, in a tilted washboard potential, I would say. So if I represent the potential U of phi versus phi, and here I have the phase, like a particle that effectively represent the phase. You see that there is a tilt because of a current, but still the phase is localized in one well. And now if I somehow shake this well, because I'm adding some alternating current, you see that the effective particle might actually jump from one minimum to the other minimum. And now if you somehow compute what is the average current, what is the mean current, so you find that, right? Delta V is delta phi over delta T. So how many flux quanta are you passing per unit time? And of course, 1 over delta T is the frequency. So using this very simple, maybe too simplistic hand-waving argument, you can show that these steps, these voltage steps, they are proportional to phi naught times, the frequency. So now our ID, this is not our ID. As I will explain, this is a very old ID, but the catch here is to say, okay, we want to use duality between phase and charge. So phase of the Josephson junction and or charge across the capacitance of the junction. And then using this duality, we should be able to build a quantum coherent effect that is the dual of this Shapiro step. So if you want to link voltage, and frequency here, you want to be in this regime. You want a large EJ over EC ratio for your junction. EJ is Josephson energy, and EC is the charging energy of the junction. You want to be able to treat the phase as a localized variable. As I said, we can represent it in the potential. It's a very well localized wave packet. Then the washboard potential is a function of phi, the flux or the phase, and you are transporting fluxons, a quantum of flux, 1 by 1 or 2 by 2 or 3 by 3, and these are the famous Shapiro steps. Now, if you assume duality works, you want to be in the opposite regime for everything. So instead of having a large EG over EC ratio, you want it to be small. Instead of having a localized phase, you want to have a localized charge. And then your potential is not a function of the phase, but it's a function of the charge or the number of carriers. This is not called this is another type of washboard potential that is usually called a Bloch band. And the cool thing is that now you would be transporting Cooper pairs and not fluxons. So this would be the dual of Shapiro steps. So as I said, this is not our ID by no means. It is definitely the work of Likarev and Zorin, something like 40 years ago. And so their bright idea suggested that it should be possible to engineer a Josephson system to really get the dual of the Shapiro step. So now let me walk you through this idea. So if you have a small EG over EC ratio or EG on the order of EC, you can show that this Josephson Hamiltonian can be easily recast to Bloch band. So you're just saying, okay, I have a periodic potential, I'm applying Bloch theorem, so I should have periodic wave functions, And similarly to what you have in electron with a periodic potential in condensed matter, you will have also a quasi-momentum that we call the quasi-charge, and you have the effective potential that is, of course, periodic, and you have several bands, right? Now, if you really want to observe these steps, you need to restrict the dynamics of your effective charge particle to one band. Similarly, again, to what we've discussed regarding the AC Josephson effect. So you want your particle to live only on this band. So for this, you need to minimize charge fluctuations and make sure that whenever you have an effective charge particle, it stays here and doesn't go there. So this is actually very challenging experimentally, and I will explain you how to do this. Just for the sake of definition, what I will call EQ in the following is the width of the first Bloch band, and what I will call delta U is the separation between the first Bloch band and the second Bloch band. So basically, you want to avoid Landau-Zener tunneling. So this is the recipe of Likert and Zorin. This has inspired a huge amount of beautiful experimental and theoretical work, 40 years of work. So I could not cite them all, but again, this has been a very hot topic for many years, and many groups tried. So the challenge is, as I said, to localize charge, and I will explain you how to do that. But before going there, I want to repeat this tilted potential picture, but in this case, it's going to be U of Q and Q. So again, now you want a bias as well, your potential, but you don't current bias, your voltage bias, and you have this potential. Here, I'm also keeping the second band. And then similarly to before, if you add an AC voltage, you might be able to transfer a charge per unit time. So if you follow exactly the same, I would say, reasoning, you can calculate the height of the current steps, and it's delta Q over delta T. So delta Q is 2e, or an integer number or times 2e, and delta T is 1 over the frequency. So you should have current steps, which are 2e times f. All right, so as I said, the devil is in the details, and more specifically, the devil is in the experimental details. Because in theory, as I said, you need Bloch band dynamics, so small EJ over EC ratio. You need a localized charge wave function, and you want negligible thermal fluctuations, so your charge particle is very much localized. So on paper, it sounds easy. In reality, this is a bit of a challenge. So to get sure you have nice Bloch band dynamics or charging effect, you need a very small Josephson junction. In the literature, it is referred to as an ultra small Josephson junction. So I will use this labeling in the following. The actual challenge is not to fabricate small Josephson junctions, because we have very nice nanofabrication tool nowadays. The challenge is to fulfill these two requirements at the same time, namely high environmental impedance and low temperature at the same time. So by impedance, I mean the impedance in parallel or seen, if you want, by the small Josephson junction. If you have a low impedance, you will have the phase as a very well localized variable. If you have a high impedance, you will have the charge as a well localized variable. And it makes sense. I could give you a full derivation, but we can use a very simple hand-waving argument. If you put a very large resistance in series with your tunnel junction, it will be difficult for the charge to tunnel. So you have something like a Coulomb blockade, if you wish. Again, it's hand-waving, but it's kind of Coulomb blockade. So you cannot tunnel. You can tunnel charges one by one only if you wish. So this is the hand-waving argument why you need very high impedance. So we could think, okay, easy, then I can just put a very large resistance in series with my Josephson junction. And people tried that, and there were some preliminary observations of these dual-shaped steps. The problem is that You also want to circulate a current that is large enough so you can measure it. And then you're spoiled by Joule heating in your environment. So simply, if you put a very large resistance in series, you pass a current, R times I square becomes too large, you cannot cool down your resistance enough, so you are not anymore in the low temperature limit, so your charge fluctuates and you don't have this well localized charge state. So then we got inspired by these two theory proposals, and they explain very nicely that actually to provide a large impedance, you don't need a large resistance. You could do it with a very large inductance as well. So it's because the impedance of a transmission line is square root L divided by C. So if you make a very large inductance and you have a very small capacitance to ground, actually you can have a transmission line without any Joule heating, because you only have a superconducting element, but still, from the point of view of the small junction, it will be a large impedance. So this is what we implemented. Our device is made of a small Josephson junction, so a small EG over EC ratio. We used a squid geometry, so it's flux tunable. And then on the left and on the right, we used very long arrays of large Josephson junction, which can be seen as inductors and with capacitances to ground. So if you want, this is a non-heating transmission line on the right, and similarly on the left. Usually in the literature, they are referred to as superinductances, so I will use this nickname in the following, but just view them as a non-dissipative high impedance. I mean, it is dissipative, but it doesn't heat up because of Joule heating transmission line. All right, so this is the device. I am an experimentalist. Maybe I should stop with theory now. And so we are fabricating what we nicknamed a block array, because it's only made of Josephson junctions. So it's like a very long array of Josephson junctions. And so here you see the junctions in blue. And in the center, we interrupted this array by two here and there small Josephson junctions, and here you recognize a squid loop. So it's fabricated in one single lithographic step to make sure that the array is as even as possible. And also the little trick here is that we used a specific substrate. Instead of using the standard silicon substrate, we used a low epsilon fused silica wafer. I think we go from an epsilon of 12 to an epsilon of 4. So we are then reducing significantly the ground capacitance. So we are, if you want, boosting the impedance this way. If you want numbers, here they are. We have an impedance of something like 8 kilo ohms, and the width of the first Bloch band is 2.5 gigahertz, and the separation to the next Bloch band, to the next band, is 8 gigahertz. So that should be high enough, to prevent Landau-Zener. And we have almost 2,000 junctions on the left and 2,000 junctions on the right. So another little novelty, but that was, I believe, key in this observation, is that we now are using a DC and microwave setup at the same time. So this is the block array. Here we have bias tube here and there. These are these blue things here and there. And so in the bottom, using the bottom arm, we can measure microwave properties. Using the top arm, we can measure DC properties. And again, at the same time, in the same fridge. And this is a close-up of the fridge. So now let's have a look at measurements. First thing we did was to measure an IV curve. Very simple measurements, I versus V, and what we observed are these nice peaks. These peaks can be understood relatively easily if you think about this array of Josephson junction from somehow a BCS / semiconducting picture. What I mean by this is that you just represent the junction as two BCS density of states facing each other. So what happened is that whenever you increase the voltage, one junction goes to the subgap state. So the current drops because it's a very high resistance, and then it remains low as long as the hole and electrons, they become aligned again, so you can flow a current, but then another junction will go to the subgap state, so the current drops again. And then you repeat this every time you reach an integer multiple of 2 delta. We are not the first to observe that. This was very nicely discussed in this paper from the group of David Haviland. Then we said, okay, do we understand this? So we somehow modified the theory or slightly adjusted the theory described in this paper. So what we did, the very simple, experimentalist level theory we did is this following. So we write just an equation of motion for this system. We have a voltage. We have, a very large inductance in series with 4 large Josephson junctions. Then we have a small junction that we model as a sign Q. So I told you about the cosine of the charge before, but since now we are dealing with the equation of motion, you need to derive the Hamiltonian ones, so you get a sign. And then we still have a little bit of damping in the system. This is 500 ohms, but this is enough cheap resistance, so it doesn't care if we don't care if it heats up or not. So if you take this
Nicolas,
system, you solve.
I'm sorry I'm disturbing you, but you have 5 minutes left.
Okay, great. I will then speed up a little bit. And if you solve this equation of motion, you recover the peaks similarly to what I've shown you before. And now, using this model, what's cool is that we can also predict what should happen if we add an AC drive to the system. And what you see is that these peaks are still there. They are slightly lower, but importantly, before them, you see nice plateaus appearing. And these plateaus, they are at 2e times the frequency. So we were quite happy seeing this. So we said, okay, let's go to the measurements and try and observe these plateaus. So as I said, a key point for us was to observe the microwave response at the same time. So what we did was to measure the microwave transmission through the whole block array. So let's say that you input some microwave here and you measure what's going out there. What you observe are these double peaks. We described that in this paper already. So, but the idea is that, given the symmetry of the system, you have 2 types of microwave modes, the odd and the even modes. And if you follow this simple cartoon, you see that the odd mode, they will couple to the small Josephson junction because there is a phase bias across the small junction, while the even mode, they decouple from the Josephson junction because there is no phase bias across it. And then what we did was to add a pump, similarly to what you want to do for the observing dual Shapiro steps. And then, of course, you need to pump at the right frequency, the right power. The phase parameter is really huge. So this is why the microwave measurements are really useful for that. So here I am plotting a 2D graph where we have the pump power on the left and the spectroscopy frequency, the VNA frequency on the right. And what you see is that if you are at the right power and at the right frequency, you see some kind of mode that is now synchronized with the pump frequency. So the pump frequency is this faint line here, and this is the block array response. And you see that right here at this power around -5 dBm, something happens. And if you now measure the IV curve without touching anything, this is what you observe. So you still have the peaks, as I told you, but now before the peaks, you have nice plateaus, which are quantized, and they are quantized as 2e times the frequency. Of course, now you might wonder, okay, are these really dual Shapiro steps? Is it really flat? So of course, we are very concerned about that. So what we did was to sit at a given voltage. So you say, okay, for example, I choose this voltage, then I ramp up the pump power, keeping the voltage constant, and I measure the current. So what you see is that the current increases, and then it plateaus, again, around -5 dBm, and then, of course, it might eventually increase further if you keep increasing the power. We pushed this analysis one step further. Instead of just measuring the current versus power, we used the lock-in amplifier to measure DI over DP, and you see that this goes down 0. The derivative, if you want, is 0 at -5 dBm. So this gave us a strong confidence that what we are observing are probably dual Shapiro steps. Now, of course, the next thing you want to check is the frequency dependent, because I promised you that this current should be 2E times F. Of course, then what you want to do is to vary the frequency. So this is what we did. Here I am plotting current versus pump frequency, and you see that we observe nicely aligned dots. But for this point, around 5.5 gigahertz, we observed steps, but they were not stable, they were jumping, so we don't know what happened, but anyway, this is what we observed. For the sake of clarity, on this large graph, I am plotting the current versus the voltage for these three different pump frequencies. So of course, code color is the same. Dark blue, light blue, and medium blue, they are for these three different guys. And you see that every time you see one plateau, and one plateau. Now, if you are interested in some more metrological performance of the device, we are very far from any metrological accuracy. Let me be very clear. Of course, this is a fair experiment, so this is somehow expected, but still it's promising, because if you plot the relatives, you see that we have well below 1% precision and accuracy for this first measurement, maybe something like a couple 10 to the -3 precision and accuracy. But again, this was not the topic, the main goal of this first study. I guess it's time to conclude. I see it's 11 on my clock. So as a conclusion, we've implemented the proposal of Likaref and Zorin. We could finally observe dual Shapiro steps, because we implemented the high impedance environment using superinductances, and also because I believe we use the DC and microwave setup. Of course, it opens many new opportunities. Obviously, we don't understand all the details, so there are a lot of physical questions. Then, from an engineering point of view, we can probably improve the array a lot, increase the current, make flatter plateaus, and of course, maybe one day we can close this electrical quantum metrological triangle. So our work is now available on the archive, and I hope you went and see Oleg's talk yesterday. There is a very beautiful work from Oleg Astafyev and Yevgeny that was published on a similar topic very recently. They are not using Josephson junctions, they are using nanowires, but I believe that their work is kind of similar to what we are showing. With this, I stop, and I thank you very much for your attention. Hello? Anybody here? Maybe, can you hear me? Okay.
Okay.
Hello?
Yeah.
Can you hear me?
Okay. So it's probably something is going on there. So.
Can you hear me?
Yes, we hear you.
We hear you. The question is whether you hear me.
Yeah, no, I hear you perfectly. There was maybe 30 seconds where there was no sound, but now I fully hear you.
Okay, so shall I continue?
With pleasure.
Yeah, okay. So in order to keep your system in the lowest band, it's not sufficient to control a J over a C ratio, but you have to have some portion of dissipation. Otherwise, sooner or later, your system will go to higher bands due to Zener tunneling, okay?
Absolutely.
Yeah, so the question is, what is the mechanism, the dominating mechanism of dissipation in your experiments? Is it due to plasmons in these transmission lines which you have on both sides of your junctions? I mean, these transmission lines formed by a series of junctions, and yeah.
Yes, absolutely. Yeah, so indeed these are transmission lines. So you have plasma modes, and then eventually they are connected to the outside world. So yeah, this is we believe the main dissipation channel. Yeah, absolutely.
Okay, and also this dissipation should lead to some broadening of these block steps. I mean, you use these dual Shapiro steps, but originally Licharev uses block steps. But anyway.
Sorry. I mean, the terminology is a bit wide. Yes.
This is not the point. The point is that if you have dissipation, you have broadening of your steps. So
yes.
you're basically saying that your dissipation is large enough to keep the system in the lowest band, but small enough not to have large broadening.
Yes.
Yeah. So this is possible. Yeah, to choose the parameters like this.
Yeah, so these are the two parameters, okay. Width of the block band and separation. So you see there is a factor 3 in between them. And when you put numbers, if you calculate Landau-Zener, it's very, very, very small.
Yeah, okay, thank you.
And now regarding maybe your question about the link between the width of the step and the dissipation, this is something we don't understand for now. That we don't know. This is an open theory question, I think. Can we link?
Well, I mean, I can comment that we have a paper with Dima Golubev many years ago, which was basically in the times of Kuzmin and Haviland experiments.
Yes,
on this
yes.
one. And so
I know there are many papers we tried and compared to our experiment. It doesn't completely fit. I'm not sure that in these papers the plasmons are taken into account properly. I mean, back in the days, this is what people were doing. So
in that case, it was ohmic dissipation, but it doesn't really matter. I would say it doesn't matter much. But we can talk later, perhaps.
With pleasure.
This is an important issue. I mean, the width of the steps.
Oh yeah, this is the next thing we want to understand, and so currently we don't. Yeah, I fully agree.
Yeah, thank you.
My pleasure.
Okay, thank you. Next one, please.
I would like some comments related with dynamical equation for quasi-charge. Yes,
one?
this one. Here, actually, last term in left side is not sinusoidal, but this one is periodical function. But you put in similar to Josephson case, to phase case, sinus pi over A and Q. But really it's different. But maybe for your purpose, this one is enough. But sometimes it seems dangerous. And the first term also, inductance is Q-dependent because of there are calculations of Alexander Zorin related this moment because of block inductance, so also periodical function of quasi-charge.
Yes. So what is the? Should I comment, or do you have a more?
This one comment, general comments.
Yeah, no. Okay, it's a comment. No, I agree. So you're right. This sign of Q is absolutely an approximation. We did that because we don't know how to do the full calculation of what you're suggesting is that this is a first Bloch band approximation, and of course we should also take into account the other higher Bloch band. I fully agree. And here, if I understood correctly, you are saying that okay, writing I mean, describing this block array as a simple inductance is also probably too simplistic. And I also fully agree. Currently, we are now trying to work out a theory to really, instead of having a large inductance, really keep the dynamics of all the junctions. But since there are 4,000 of them, it's a bit of a challenge theoretically. But yeah, I fully agree. Sign Q and treating the array as an inductor is definitely too simplistic. Did I get your comment correctly?
Yes. Yes, thank
Okay.
you. Okay, thank you, Nicolas. So I am
Thank you
sending
very
your
much.
certificate from the online. You may see maybe. So
And
thank you.
thank you very much. I stopped sharing.
Okay, okay. So next speaker is not here. So I'm closing the session. Thank you.
Gusikov Institute of Radiophysics and Electronics of National Academic Sciences of Ukraine. The theme of my presentation is large photon magnon coupling in a P-shaped resonator with a magnetic sample. Now there is a great interest in the area of quantum information technologies. One of the problems in this area is information transfer from over a large distance with preserved covariance. This requires the development of quantum converters of electromagnetic radiation from microwave to optical range. For example, such converters can be based on electromagnetic resonator with the magnetic sample under the ferromagnetic resonance conditions. In such system, the key parameter is the photon magnon coupling strength. Thus, the purpose of work is to increase the photon magnon coupling strength between a planar microwave resonator and spin system of magnetic sample. To solve this problem, we proposed to change the conventional microstrip resonator by giving it the shape of the letter P. The feeding microstrip line and the resonator made of microstrip line of small width and small gap between these parts of resonator. This system placed on the substrate with metallization below. Here is some parameter of resonator. The resonance frequency of such resonator is about 6 gigahertz. On the surface of this resonator, on the gap between two parts of this resonator, near its band, we place the magnetic sample. This is yttrium iron garnet film with such size. The thickness of yttrium garnet film for calculation was 10 micrometers. The direction of external DC magnetic field was chosen across the microstrip line, along the y-axis. This direction of magnetic field corresponds to typical conditions of ferromagnetic resonance, where the DC magnetic field and alternating magnetic field is normal to each other. To calculate the spatial field distribution of magnetic field intensity near the resonator surface, we use finite element method. In this work, we obtain only numerical results. As well, we calculate also transmission characteristics of such system where the feeding microstrip line is 2-port systems, and we calculate S to one parameter. Here you can see this special field distribution of the normal magnetic field component on the resonator plane. The frequency is about 6 gigahertz. It's resonance frequency for this resonator. The resonator fit about half of wavelengths. This mode is the lowest mode for such resonator. As we can see from the field distribution, the alternating magnetic field is concentrated near the band of the resonator. Also, the fields summarized in such system in the gap of this resonator is, and the largest value is near the band. Then we place the yttrium iron garnet film on this area. If we place the sample in this area, we can obtain the large photon-magnon coupling strength. To obtain the photon-magnon coupling strength value, we calculate the transmission coefficient, the amplitude of wave propagation through the feeding microstrip line that connected with our P-shaped resonator with magnetic film. And we change also the external magnetic field strength, DC magnetic field. Then we obtain a two-dimensional color map graph. Here we can see the horizontal line is the resonator mode. Also, we can see the ferromagnetic resonance mode. And this mode in such system graph, we can see the anti-crossing effect of this mode. On the resonance magnetic field, DC magnetic field, we can obtain the distance between these modes in frequency units. And this distance between the mean of the transmission coefficient spectrum is approximately equal to the doublet value of the coupling strength. Also, we calculate the spin number normalized coupling strength by this formula. Here, Ns is the number of spins in magnetic sample volume. The concentration was chosen here for the yttrium iron garnet monocrystalline sample. Here we obtain such values of coupling strength, 211 megahertz, and spin number normalized coupling strength is about 1 hertz. This is a quite large value. For example, for the usual square split ring resonator, that operate at frequency 6 GHz. The coupling strength is about 5 times smaller than for our P-shaped resonator. Thus, it was numerically found that photon-magnon coupling strength reach a very large value for such system of P-shaped resonator with a magnetic sample, up to 1 Hz. This effect can be explained by the fact that alternating magnetic field summarized near the band of the resonator and achieves maximum in the this space area. Here we obtain that if we want to increase the photon-magnon coupling strength, we also can increasing the filling factor of the magnet by the alternating magnetic field. For this resonator, we place the sample on the large fields, alternating magnetic fields, and our filling factor is reaches quite large value. That's all. Thank you for attention.
Dear Sergey, thank you for your presentation. And some questions, please, from internet, maybe from live persons. Maybe I would like to ask you about some equations related with electron-magnon coupling. What was the general expression which you are using in calculation of these numerical results? This one, maybe any reference, any papers you can.
Spin number normalized coupling strength or general parameter. The coupling strengths which we found from these results can be obtained if we know some parameters of the system. For example, filling factor, it's directly proportional to the coupling strength. Also, frequency of resonator, number of spins, and concentration of spins. This maybe 4 parameters is the proportional to the first or square root of these parameters can influence to the coupling strength.
Hi. Yes. Yes. Thank
If
you.
we have large concentration or large number of spins, we can increase the coupling strength. Also, the filling factor is proportional in first. Is the main parameters maybe.
Yeah, yes. Yes, thank you, Sergey, for your presentation. Here, organizing committee will send to you your certificate of attendance to conference in online in email. And no another questions. Maybe it related with that today in this section, last section, and some people's going away, and I think that it will be a nice presentation, and thank you again. You are from
Okay.
Kharkiv, yes, yeah? You are Kharkiv?
Yes, I'm.
Yeah.
Yes.
Although it was nice to meet you. Thank you again.
Thank you.
presentation will be given down by Mitun Ghosh from India. Please, you have 20 minutes. 20 minutes.
Good afternoon, everyone. So first I thank this ICQMT organizing committee for giving me opportunity to present our recent publication in this nice conference. So I am PhD candidate and I am working under Professor P.S. Anil Kumar in Department of Physics, Indian Institute of Science, Bangalore, India. So the title of my topic is talk is that momentum space and real space barycurvature induce Hall effect in magnetic or semimetallic U2 07 111 epitaxial thin film. So okay. So the compound is belongs to the pyrochloroiridates family. Like A side you can put any kind of rare earth element, and the B side is 5D element iridium and oxygen. So if you see the phase diagram, in plane of electronic correlation U and spin orbit coupling lambda. So there is, depending on the relative strength of U and lambda, there are multiple electronic ground state. So if you consider 3D element where electronic correlation is high, whereas due to small atomic number, means small Z value, the lambda value will be low, so you will go towards the more insulating side. But iridium is 5D element, where we have extended orbital, that's why the electronic correlation will be low, as well as high Z value, that's why the spin orbit coupling will be high. So and their relative value will be relatively close to each other. So we'll landed near to the semi-metallic phase, like this oil semi-metallic phase that is predicted by theoretically. Now if you consider the variation, now if you vary the A side cation radius, like if we go to, as we go to higher atomic radii, what will happen, the sample will become more metallic. Like this particular series have metal to magnetic insulator transition temperature, like thermally driven transition. But if we increase the ionic radii, what will happen, the sample will become more metallic, and in the lower ionic radii, the higher temperature region will be non-metallic, whereas the low temperature will be magnetic insulator. So since we are trying to probe the oil semi-metallic nature, so our most interest will be near to this, like this EU, SM and ND, where we can see this metallic behavior at high temperature and insulating behavior in the low temperature. And not insulating, it will be like semi-metallic behavior. As we process, we can like explain how it is different that insulating behavior. Okay, so this is electronic phase diagram in space of U and lambda. Now people have theoretically calculated the band structure, and so it will have some 3D crossing point inside the band, inside the electronic band, and this crossing is called wild node. It is different the Dirac node, where the spin or spin degeneracy is not broken, but for this particular case the spin degeneracy will be broken. And if we get the projection of this billiard in the Fermi surface, we'll get like Fermi arc kind of density of state. So it is called Fermi arc in the surface of the billiard. Okay, so this all about electronic structure of this material. Now if we consider the spin structure of this material, like if you look along the body diagonal of the unit cell, will have this corner sharing tetrahedra. So there is two cation, like one cation will be displaced from each other like half of the unit cell. And if we start putting the magnetic moment on the cation, due to this geometrical structure, the magnetic moment will be either parallel to the local 1-1 axis or antiparallel to the local 1-1 axis. So basically we will have two kind of domain structure. Like in this domain, all the spin are towards the center of the tetrahedra, and the bottom tetrahedra, all the spin are away from the center of the tetrahedra. So we call this as a all in, all out, whereas this domain we call as a B domain, all out, all in. And at zero field, both are equally probable. So sample will have like equal distribution of the both the domain. So this is all about the magnetic structure of this material. Okay. So now, as we process our measurement, we will try to probe both the electronic structure as well as the magnetic structure of the sample through the help of magnetotransfer measurement. Yeah. So we have studied the sample in thin film geometry. So the substrate we have used YSZ11 substrates, as the lattice parameter of the sample and substrate is close to each other, like double of the lattice parameter of substrate and lattice parameter of the sample is close to each other, and if we calculate the lattice mismatch, it will come 0.3%. So since for thin film the surface of the substrate is very much important, that's why we did the treatment of the substrate also. Like this is the AFM image of the as received, means commercially bought substrate. So you can see a lot of island kind of feature and rough surface. So if we do heat treatment like annealing at 1200 degrees centigrade for 2 hours in air, we'll get nice stress structure. So this is the corresponding AFM image. So it have step with a 0.3 nanometer, which is kind of spacing along the D11 direction, and with some almost 100 nanometers. So the miscut angle will come around 0.15 degree. Now we'll go to our sample preparation. So since iridium have a lot of tendency to have going out of the sample, like due to the formation of IRO3, which is volatile in nature, what we used 3:1 target instead of stoichiometric target, and we evaluated the target material, and this our sample preparation is kind of two-step process. Like since this pyrochlorophase form very high temperature, so if we grow the sample at high temperature in the PLD process, we will not be able to stabilize the phase. That's why what we did, we anneal the sample in some higher temperature where the phase is forming, and this is the corresponding structural analysis. So first figure which is the XRR, which confirm the thickness, then this is the XRD figure. So the presence of the odd peak confirm the pure phase of pyrochloro rather than any impurity phase. And to check the strain or relaxed growth, we have done reciprocal space mapping. So this is this reciprocal space mapping tell us it has strain growth and its cubic symmetry is broken in the sample, so which will help us to explain other result. Okay. Now this is the oxidation state. We have checked the oxidation of both the cation like U3 plus and IR4 plus. So we saw that the IR4 plus is not iridium don't have only one single oxidation state, rather it have two oxidation state, 4 plus and 3 plus, and we assign that it will be might be due to some oxygen of stoichiometry in the sample, whether you have only one oxidation state. Now we measure the resistivity versus temperature. In the high temperature region, it have metallic behavior, whereas there around 90 Kelvin, it have going to the insulating behavior, but the insulating does not follow any activation law, rather it follows some power law, T to the minus alpha. That means it is kind of gapless semi-metallic feature. Now this transition is related to some microscopic change in the IROC octahedra parameter, like IRO oxygen bond or IRO oxygen length, that is changing with the temperature variation. That's why it is reflected in the transport. Now when we are studying the sample, we already had some knowledge about how to tune the semi-metallic charge transfer. So people have done the variation in the charge transfer by applying physical pressure, like the report by Tapti et al. In 2012. What they did, they started applying hydrostatic pressure on the single crystal, and if you saw, as we increasing the pressure, their resistivity value is dropping. That is, it is becoming more metallic. That means there is change in the lattice parameter is occurring. That's why hopping is changing. That's why they are getting more metallic. Similarly, in the paper by ICQMT et al., what they did, instead of hydrostatic pressure, they changed the stoichiometry in the sample. And if you see, as we increase the iridium content in the sample, the metallic nature is also increasing. So this is kind of physical pressure. This can be called chemical pressure. So our idea was that whether we can tune this semi-metallic charge transfer in thin film geometry. So what we did, we go through different thickness sample, like this is 30 nanometer, 50 and 70. We saw that the XRD peak is shifting towards the left. That means lattice parameter is increasing as we're going to lower thickness sample. So lattice parameter can change due to two reasons. Either it can have systematic change in the strain or systematic change in the lattice parameter. So what we did, we took help of the reciprocal space mapping, and we see that all the sample have similar strain. Like all the sample have similar lattice parameter in plane, whereas the whatever change is occurring, that is occurring in the out of plane. That means strain is not playing role, only the stoichiometry is playing role here. That's why its peak position is shifting towards lower value. That means lattice parameter is increasing. Now if you see the transport properties, so the red curve is the transport for like normalized resistivity versus temperature plot. That is for 30 nanometer. So in 30 nanometer, we are not seeing any metallic behavior in the high temperature, rather than it is started increasing from the 300 Kelvin and going up to 2 Kelvin. So we are missing the metal insulator transition for 30 nanometer. Rather, if you see the 50 and 70 nanometer, we can see nice metallic behavior at the high temperature region and nice change in the slope at around 100 Kelvin. So this is the derivative plot to capture the transition temperature. We took help of the slope of the high temperature derivative and low temperature derivative, and you can see the systematically change in the transition temperature is occurring. Now we fitted the low temperature data like 2 to 25 Kelvin in the some power law like ln rho versus ln-t, and we fitted with nice straight line. So if we put the coefficient alpha versus thickness, we can see it is decreasing as we increasing the thickness. That means its resistance is decreasing as we increasing the thickness. So this is also playing similarly as a chemical pressure in the sample. Okay, so basically we can tune the metallic behavior in the sample by changing its thickness. So yeah, so now we focus on the around 60 nanometer sample and did all the transfer properties in the detailed transfer properties measurement. So this is our Hall data at 4 Kelvin. Just measure Hall data rho xi versus field, magnetic field. So you could measure up to 9 Tesla. Sorry. So after subtracting the ordinary Hall component, we can see the presence of extra component. So we termed this as an anomalous plus topological component. So similarly, we plot the data for different temperature from, and the extra components start appearing from 25 Kelvin onward. So if we see it is coming and it increasing the value, but at 10 Kelvin it is kind of smooth variation and getting saturation, but the low temperature like 3 Kelvin onward, it has some hum kind feature, then saturation, and it is more prominent at 2 Kelvin. So this might be coming due to the some extra component rather than anomalous Hall component. So what we did, so actually this for magnetic material, this anomalous Hall component can come from magnetization also, but in our case this is an antiferromagnet and its magnetization is very low, only the field induced magnetization is occurring. So to rule out the magnetization origin, we have plotted the anomalous Hall resistivity like this blue curve along with the major magnetization at the red curve. So you could see that there is no one-to-one correlation. So the magnetization origin is not the only origin, rather than some extra origin is coming which we assign that momentum as Berry curvature rather than the magnetization origin. So this our anomalous Hall measurements confirm that there might be some linear crossing point inside the billion which is acting as a fictitious magnetic field, and we are getting extra component in the anomalous Hall component, anomalous Hall resistivity. Okay, so there is now standard rule to kind of see the mechanism of the anomalous Hall conductivity, like the scaling relation, rho xy saturation versus rho xx. So we have plotted the saturation resistivity versus rho xx at zero field, and you can see that it is following some power law like rho xx to the 1.6. That means the intrinsic origin is depressed by suppressed by the presence of disorder in the material. But this is a color plot of the rho xy He plus Thi and Ht plane, like field versus temperature. So you can see in the low temperature and high field region, the anomalous Hall resistivity is high, but here we can see the little drop. That means that this Thi signal is dropping in this region. That's why it is coming little drop. So the phase space we divided in two parts. So the low temperature high part we mention at a WSM. WSM means oil semi metal, Whereas the high temperature region, we mentioned that all in all out semi-metal, because the magnetic order is present, but the oil nature is not presenting here. That's why we call it as a all in all out semi-metal. Yeah, so this confirm as a fingerprint. This anomalous Hall resistivity measurement is confirm the means gave some identification or what to call this some feelings of the presence of oil point in the material. That means it confirm the fingerprint of oil semi-metallic phase in this particular compound. So we have measured some other sample also. So this interesting thing, in addition to non-linearity, we are getting some hysteresis also, like in low temperature. For one sample, we got 3 to 2 Kelvin. Other sample, we got almost 7 Kelvin the hysteresis. Whereas there is no hysteresis in the magnetization. So that is solely governed by this momentum space Berry curvature. Now we'll now our interest will be the real space Berry curvature, like topological Hall effect. So what we did to extract the topological Hall component, we have fitted the 10 Kelvin Hall data where only the anomalous Hall component is present, and this red curve is a fitted curve with some empirical formula like odd polynomial. So we just use the odd polynomial and scale it out to capture the smooth variation of this 2K data, and we subtracted the black curve from the red curve, and we got this THE component. So this THE component, we can see it is varying, means it is increasing the low field region and getting saturated around 50 kilooershad, then dropping in a high field region. So this non-monotonic variation we can explain with the simple models. So since our material have non-coplanar spin structure, so if we see 3 spin, like 3 nearby spin, Si, Sj, Sk, which is close some like triangle, and some conduction electron towards this path like Si, Sj, Sk, it will acquire some extra Berry phase, which will be proportional to the solid angle of the 3 spins. So Si dot Sj cross Sk is called scalar spin chirality. So at the zero field, we have both kind of domain. So and their corresponding spin chirality will be equal and opposite, so it will cancel out. That is mentioned here like with the simple model. But as we increasing the field, so there will be asymmetric canting. That's why you have non-zero spin chirality in particular direction, and that's why it will increase and it gets saturation. And what will happen when you apply large field, their angle will try to close. That's why the solid angle will drop. That's why you are getting decreasing in nature. So what we mean real space Berry curvature is that since the spin structure is in the real lattice, so we call this the spin chirality into real space Berry curvature causes our large THE. Now we'll go to our magnetoresistance measurement. So for our sample, we have applied the field along the 1-1 direction, and magnetic lattice have the 1-1 direction. So this green curve is the zero field measurement. Like we just cooled down the sample up to 2 Kelvin, then we apply field and did the measurement. So if you see the green curve, it is symmetric in the both positive half and negative half. Whereas the red curve, what we did, we apply 14 Tesla field at room temperature or above the magnetic ordering temperature, and we cool the sample. So we can see nice asymmetric in the positive half and negative half. Whereas in the negative, blue curve, we apply minus 14 Tesla field and cool the sample. So we can see the asymmetry reverse the sign. So here we plotted the asymmetric component like red versus green, and this green curve shows that there is no asymmetry. Asymmetry is 0, but red and blue curve shows the asymmetry is reversing sign when you are changing the field direction. So means that we are able to stabilize one kind of domain in the material by field cooling. Instead of zero field cool, if we cool down in some positive field, it will stabilize one domain, and if we cool down in negative field, it will stabilize other domains. So this measurement confirms the bistability of the single domain in the material. Okay, so now if we go to details of this earlier measurement was at 2 Kelvin only. Now if we go to details measurement at different temperature, what will happen at from 2 Kelvin to 10 Kelvin, MR is negative and symmetric in both direction, and there is no hysteresis. But interesting, the low field region, the MR is more or less behaving quadratically, whereas high field region it is linear, which is captured nicely in the derivative plot. Now if we go to intermediate temperature, like height 15 to like transition temperature, what will happen? In the low field region there is positive MR and high field it is negative MR, and there is nice hysteresis between the two field sweep, like up sweep and down sweep. So we explain this up sweep and down sweep in terms of field induced change in the spin structure. So the first we took the help of this simple model, like H is the Hamiltonian for the spin, whereas this SI dot Sj is the antiferrometric exchange interaction between the two spin, and this second term is the due to field induced Zeeman energy. So what will happen when there is some temperature, this term will have a weak contribution, rather than this field induced Zeeman energy will have large contribution. So some spin will flip and make some other magnetic structure. So and there will be like imbalance of the domain, like both A and B domain. So positive field region, the A domain will be maximized, whereas negative field region, B domain will be maximized. So that is gives us a finite hysteresis between field upsweep and down sweep. Now this and this hysteresis and this hysteresis is present up to 80 Kelvin, where is the transition temperature. So it confirms that there is subtle interplay between the antiferrometric exchange and Zeeman energy, and this spin as well as the domain structure is plays significant role in the magnetotransfer properties. So to summarize our result, that we can tune the charge transfer by varying the thickness of the sample, and this anomalous Hall effect is governed by the momentum space Berry curvature, and this topological Hall effect is mediated by the real space Berry curvature due to the non-coplanar spin structure. And this magnetic field induced modification of the spin structure is change the spin structure as well as domain distribution, which causes us asymmetric and hysteretic magnetoresistance. Okay, so I acknowledge all the funding agencies and my collaborator like Dr. D. Samuel and Dr. Sweta Bhatt and Dr. Anand Pal, and finally thanks for your attention. Actually, here what is happening, sorry. Yeah. So the thing is that the sample have lot of sensitivity of the iridium IR. Like if you go to the earlier report, if you see that there is iridium content is changing from 1% to 3%, and the resistivity dropping from 10 to the 4 to 1. So since our sample have thin film and we are growing at high temperature like 1000 degree, so when our thickness smaller, so more iridium will have tendency to go out of the sample, because iridium will become IRO3 in the presence of oxygen, and it have tendency to go out of the sample. But when we make some thick sample, more iridium will be contained in the sample. That's why this iridium content will be like balanced when we grow the thick sample. I think the composition will change a lot when we grow the lower thickness. That's why we will not be able to conclude whether this is dimensional dependent or. Yeah. Magnetoresistance trend and behavior will be similar, but absolute value can decrease and increase. So because this IR, the spin will be like when you have impurity sample, so the network will be disjoint or kind of, so value can decrease also and increase also. So that is little bit like a kind of very much stoichiometry sensitive, this compound particularly. Like even people have done this single crystal study also, they are not able to get this particle. Like here they are getting nice transition, but if you see this study, they are not getting nice transition.